Hey everybody, welcome back. Today, I'm going to be going over how to approach an MCAT passage. Specifically, I'm going to be doing one that's called Aldehydes and Ketones, which is an organic chemistry-based passage. So I'm just going to be going over how I read the passage, what I tend to focus on, the things I consider to be important, and then what my logic is when answering the questions. So all these passages can be found on Khan Academy, which is a great resource. If you are not using it, I do recommend you check it out. So let's get started. Aldehydes and ketones. It says, methanol poisoning is a medical emergency. Methanol is converted to formic acid via formaldehyde. Now, when you guys are reading things like this, make sure that if you see any diagrams, you pay attention to them. So it says, methanol is converted to formic acid via formaldehyde. So methanol turns into formaldehyde, which turns into formic acid. Okay. With formic acid being the toxic metabolite that causes damage to the optic nerve, leading to permanent blindness. So formic acid is the poisonous substance in this series. Oral ingestion of methanol-containing mixtures require immediate medical attention. Once ingested, peak serum levels occur within 30 to 90 minutes. Now, things like this you can typically ignore. If you are familiar and if you know that this is a chemistry-based passage, I really doubt that information like this would be useful, because this seems more biologically relevant. So I don't see how they could incorporate this into a chemistry passage, but that's just my thought process when reading. So continuing on, methanol is metabolized in the liver in sequential steps to formaldehyde by first by hepatic alcohol dehydrogenase, then to formic acid by formaldehyde dehydrogenase, and then finally detoxified as carbon dioxide. So to break this down again, let me clarify something. It says methanol is metabolized in the liver in sequential steps to formaldehyde by hepatic alcohol dehydrogenase. So this first enzyme that they've given, you have to recognize that it's number A, or it's this one right here. And the second one that they mentioned, formaldehyde dehydrogenase, should be B. I like to take notes of things like this because if they are checking certain details or specifications in the passage, they might ask you, oh, what is enzyme A or what is enzyme B? So little details like that, it doesn't hurt to know. So just keep things like that in mind. Okay, and then it's finally detoxified as carbon dioxide and water. The slow conversion of formic acid to carbon dioxide forms the basic of methanol toxicity. So it's the conversion from the formic acid to the carbon dioxide, which occurs too slowly, which causes its toxicity. And as we can read here, it says metabolic acidosis and tissue injury. It says, in the lab, methanol can be converted to formic acid via a series of chemical transformations. The chemical process is summarized in the schematic presented in Figure 1, which is this. A student proposes to replicate this chemical pathway and performs 2 trials, but obtains varied results. Okay, now that we have all this in mind, they're going to be obviously going over 2 trials, but while you are reading this, I'm assuming that you're going to have to keep referring back to this diagram, so keep this in mind when you're reading the next 2 trials. So trial 1. At the beginning of the experiment, the student mistakenly uses isopropyl alcohol. Well, that's definitely something you should highlight the second you see it, because the student made a mistake here. So I'm assuming that the questions are going to be based on this error that the student made. Instead of alcohol, or instead of methanol, he succeeds in converting isopropyl alcohol to an unknown substance using pyridinium chlorochromate, or colochromate, which is PCC, and in DCM, which is dichloromethane. In your review, you should have learned that these 2 substances, PCC and DCM, DCM being the solvent, are used for oxidation, and specifically oxidation of alcohols, which is what we're given in the beginning. Okay. This is the same procedure for formaldehyde formation from methanol. So it's the same procedure that's given up top here, except the student used the wrong starting reagent. However, this unknown substance demonstrates different properties than what he expects from formaldehyde. Well, obviously that's given because he used a different starting reagent than what he was supposed to. Okay, so trial 1, a student made an error and used isopropyl alcohol instead of methanol. In trial 2, the student follows the same protocol with PCC and DCM as trial 1, but the proper starting reagent of methanol and successfully forms formaldehyde. He proceeds to add Tollin's reagent, which is silver oxide, dissolved in aqueous ammonia, to the formaldehyde, successfully yielding formic acid. So in trial 2, the student performs essentially just this series of steps correctly, and in trial 1, they use the wrong starting reagent. So now that we know everything, let's see how we can answer these questions. What is the simplest way that the student can confirm the successful formation of formic acid using Tollin's reagent in trial 2? Well, trial 2, the student uses the correct starting reagent, being methanol, and the only detail that you have to be familiar with here is what is Tollin's reagent. Although it's given here, you have to know from your review what it is, what it does, and what its function is. So I believe for the MCAT, the few indicating reagents that you need to know is a Tollin's reagent, Benedict's reagent, and Fehling's reagent, I believe. But essentially what it is, it's a way to detect if an oxidation has occurred. So, since we know that it's silver oxide, which is used to convert the formaldehyde to formic acid, what's going to happen is this oxygen that's present within the silver oxide is going to attach to this hydrogen to create an alcohol group to form the formic acid, which means that you will be left with just the silver precipitate, which should precipitate out into your solution and should become visible. So ideally, given that you understand what Tollin's reagent is and what its function is, you should be familiar that it should cause, when an oxidation occurs, like in the conversion of formaldehyde to formic acid, silver should be precipitated into the solution. So let's read our answers. By measuring the density of a liquid and comparing it to published values. Well, yes, you could do that, although I don't know how. You would have to first of all determine the density of your reagent, and it's not the easiest. This would definitely work, but it doesn't seem like it's the easiest way to approach this. By noting characteristic sharp odors emanating from the tube. Well, that's not a very precise way to determine what a reagent or a chemical might be, because usually the scent is given due to certain functional groups that are present. So formic acid might have a similar scent to another carboxylic acid that's maybe an extra carbon long, for example. So again, this is not a good way to detect it. By boiling the liquid and comparing the boiling temperature to published values. Yes, you could also do this, but again, it's not the easiest because it would depend on how pure your substance is, how exactly you measure the boiling point, because usually the literature values are precise. So it depends on how well you can perform this boiling and all that. So again, possible, but not the best approach. And D, by observing the silver deposition in the tube, which is correct because that's what it says Tollin's reagent is. It's when you have silver oxide dissolved in ammonia. So I'm going to say that this is the answer, and it is. So that brings us to question number 2, which asks, do you expect the unknown substance synthesized in trial 1 to form a carboxylic acid compound, such as formic acid in figure 1, more or less easily than formaldehyde, and why? So before I approach this question, it's important that I look at this series of steps. So in this series of steps, we have a primary alcohol that's converted into an aldehyde, which is then oxidized into a carboxylic acid. But what happens in trial 1? We know that whoever ran this trial used isopropyl alcohol instead of methanol. So let's draw out the series of steps that happen. And this is a public service announcement to you guys. You should know how to draw all these things, just given the name or given the chemical formula of it. So that is your isopropyl alcohol. And you can see when you compare it to the methanol, It's similar in terms that it's an alcohol, but these two hydrogens have been replaced with methyl groups. So that is the only real difference between them, but it obviously will change its reactivity and its ability to turn into carboxylic acid. So in the next step, as it shows here, it says that the isopropyl alcohol was exposed to PCC and DCM. And essentially, if you know your organic chemistry, these two things are oxidizing agents. So what they do is they convert your alcohol group to a double bonded oxygen. So that will convert that into CH3, CH3. Now, this is what we're left with. So unlike this aldehyde, this formaldehyde that we formed, that had these two lone hydrogens, we actually don't have any lone hydrogens here. So this last step that involved oxidizing one of these hydrogens, essentially, attaching an oxygen to them, if you want to think of it really simply, although the mechanism is not that straightforward. This doesn't have anything that can be oxidized. This compound cannot be oxidized further. Can't be oxidized. At least not in a very conventional way. You could oxidize it if you manage to get rid of one of these methyl groups on the side, but in its current form, it can't be oxidized any further. So let's read our answer choices. The unknown substance synthesized in trial 1 will form a carboxylic acid more easily than formaldehyde due to the lack of lone hydrogens attached to the main carbon in the unknown substance. Well, we know based on this information that the isopropyl alcohol group cannot be converted into a carboxylic acid just due to the nature of the fact it doesn't have any lone hydrogens. Because it can't be converted into a carboxylic acid in the first place, obviously the answer you should be looking for is that this unknown compound will form a carboxylic acid less readily. So this answer choice says that the unknown will form carboxylic acids more easily, which we know right off the bat is incorrect. Answer choice B asks, the unknown substance synthesized in trial 1 will form carboxylic acid compounds less easily than formaldehyde due to the lack of hydrogen attached to the main carbon in the unknown substance. So that sounds correct, because it says the two things we need to know, which is that it will form carboxylic acids less easily, and it will form them less easily due to the lack of a lone hydrogen on the main carbon. So that seems correct, but let's just continue with the answer choices. Answer choice C says that the unknown substance synthesized in trial 1 will form carboxylic acid compounds less easily than formaldehyde due to the presence of a lone hydrogen in the main carbon of the unknown substance. Well, if we had a hydrogen here, for example, then it might be possible to convert it to carboxylic acid, but then we would have 5 bonds, which makes absolutely no sense. So no, that answer choice is not correct, because what the issue actually is that we're missing a lone hydrogen that's present in formaldehyde but not in our unknown. So that's incorrect. And answer choice D says the unknown substance synthesized in trial 1 will form carboxylic acid compounds more easily. Just because it says more easily, we know right off the bat, not correct. So I believe that that's the answer, and it is. Which statement is true regarding the physical properties of methanol and isopropyl alcohol? So between this methanol and the isopropyl alcohol that we had here. So reading the solutions, boiling point solubility, it's going to be pertaining to, the boiling point and the solubility. So let me draw the two side by side. So we have methanol here. And I'll have to draw my isopropyl alcohol again. Sorry about that. Okay. Let's go over the answers and see if they're correct or not. Methanol has a lower boiling point and solubility in water than isopropyl alcohol. So it is important that you note that all these solutions are given in terms of water, because the answers might differ if they're given their solubility and boiling point in something that's nonpolar. So, does methanol have a lower boiling point and solubility than water? In water than isopropyl alcohol. Well, let's just forget about the solutions for now, and let's just focus on these two compounds. Which one do you expect to have a lower or higher boiling point, and which one do you expect to have a lower or higher solubility in water? So let's focus on solubility first. And the golden rule for solubility is like dissolved like. And most of you should be aware of this by now. So since we know they're asking about the solubility in water, and you know that water is polar, essentially it's asking which one of these two compounds is going to be more polar, because whichever one is more polar should have the higher solubility inside water. Now, both of these have OH groups, which should realistically form hydrogen bonds with water, but this isopropyl alcohol has two methyl groups attached to it. And these methyl groups are organic and they're nonpolar, so it will make the entirety of this molecule less polar than the methanol. And because of this, we know that methanol should be more polar. Sorry about my writing. Polar. We know that the methanol should be more polar than the isopropyl alcohol. So, given the rule, like dissolves like, methanol should have a higher solubility in water than the isopropyl alcohol. So, reading our solutions, methanol has a lower solubility, so this has to be incorrect. We have to look for answers that says methanol has a higher solubility. So, the A is incorrect. B says methanol, higher solubility. That could be true. C says methanol, higher solubility. That could also be true. And D says methanol, lower solubility. So, that's not true. So, we can just cross out A and D. And now we're left with B and C. Now, about boiling point. Boiling point is a little trickier, so let me explain. The thing with boiling point is you do have to take polarity into account as well, in the sense that if something has higher intermolecular forces, it will also have a higher boiling point, just because of the fact that things will be able to bind to each other tighter. So in these two substances, both of them have an OH group, and you should know that OH groups are capable of hydrogen bonding with each other. So this isopropyl alcohol will hydrogen bond to something like this. Sorry for this slow drawing, but as you can see, these are two isopropyl alcohol groups. I just flipped this one around just so you can match the O and the H. So hydrogen bonding occurs between a hydrogen bonded to an oxygen, nitrogen, or a fluorine. So hydrogen bonding would happen here, but it would also happen in the methanol. So both of these compounds experience hydrogen bonding, meaning that they experience the same intermolecular forces. But the difference comes in this methyl group. Now, since this methyl group is present, the isopropyl alcohol also experiences what we call van der Waals forces, or some of you might call them dispersion forces. Essentially, what they are is the bigger the carbon chain you have. One second. The longer your carbon chain, essentially, what they can do is the carbons can somewhat stack on top of each other to form really weak bonds with each other. And because of this, this gives the isopropyl alcohol a slight advantage in terms of its intermolecular forces, because both of them experience the hydrogen bonding from the alcohol group, correct? But the isopropyl alcohol also contains these methyl groups, which are able to use these van der Waals forces to kind of stack somewhat on top of each other and form these weak associations that might help its intermolecular forces be a bit tighter. And because of this, the isopropyl alcohol should have a slightly higher boiling point, because it's experiencing two sets of intermolecular forces, being the hydrogen bonding and the van der Waals forces, whereas the methanol only has the hydrogen bonding available from the alcohol group. So methanol should have a lower boiling point and a higher solubility than isopropyl alcohol, which is correct. Okay, choose one answer. Okay, this one's pretty straightforward. This is asking, is this an oxidation or a reduction? And the easiest way to do this is, if something is adding an oxygen or decreasing a hydrogen, it is an oxidation. And if something is doing the opposite, it's a reduction. So now, going from the methanol to formaldehyde, we had an OH group that turned into a double bonded O, so to form an formaldehyde, to form an aldehyde, that is. So what we had to do is we had to kind of get rid of this hydrogen group. Now, if we got rid of a hydrogen and increased the bonding to oxygen, it is an oxidation, which is pretty implicit in the name. Given that, since we know that step A is an oxidation, we can just get rid of these two because they say A is a reduction. Now, going from here to here, it's the same thing somewhat. We have a hydrogen, and what we're doing is we're increasing the number of bonds to an oxygen because we've added this oxygen here. So where there didn't used to be an oxygen, we've added an extra oxygen, which means this is also an oxidation step, which would mean this. Nice. Another way you can think about this, if you are familiar with your biochemistry, it says that the enzymes used in these conversion steps, I believe it says alcohol dehydrogenase and formaldehyde dehydrogenase. Those of you who are familiar with your biochemistry, you should know that dehydrogenases are typically used for oxidations because, as the name implies, they're dehydrogenating, which, again, implicitly in the name means you're oxidizing something. Just a little hint. And the last question is, what is the unknown compound product in trial 1? Okay, so like I had drawn before, I will draw it for the 4th time. Sorry. It's a little difficult to draw in this. So we had this, which was the isopropyl alcohol. We added PCC and DCM. So PCC and DCM are, again, oxidative agents, so what they can do is they can convert an OH group into just a double bonded O. So that will bring us here. Okay. Now that we're here, what can happen is the last step involves the conversion of this into a carboxylic acid. Well, it can't. Unless you lose one of these CH3 groups, it can't be converted into carboxylic acid. So essentially, it's just going to be left in this state. It can't go any further because what happens in here is you have these two lone hydrogens, which can be oxidized to form this carboxylic acid, but in this example, that's not an option. So this would be your final product, and given our answer choices, propanone is the answer, or the other name for this is acetone. You guys should know that name if you've been in a bunch of organic chemistry labs. So this is acetone, or you would know it's propanone as well because prop meaning 3 carbons. So you have 3 carbons, and none is the suffix for ketones, and this is a ketone. So I believe that will be the answer, and it is. Yay. Alright guys, well, that was my video for you guys today. Let me know if this was useful, if you want me to do more videos like this to kind of explain how to approach these type of MCAT questions and how to approach these passages. And if you would like to see other topics covered, please let me know in the comments below. Thank you.